and today we're going to talk about how we're using microservices and our road to of migrating from a monolith to a more microservice-based architecture. So that's essentially the first part of this presentation, and then we have a second part where we will do some more deep diving into Kubernetes. Has anyone heard of Kubernetes before? Okay, cool. Is anyone using microservices? Okay, that's good. So you will have to, if you have any questions or anything, just ask away, or if I say something, stupid, which happens, just interrupt me and, correct me. I don't know everything, but, the agenda will look something like this. So we will just briefly mention what Parkster is and why we're using microservices. And when we're talking about why we're using microservices, we will also talk a bit about what microservices is and their pros and cons and all those kind of things. And we will talk a bit about organizational or team structure as well, just a little bit. And then we'll talk a little bit about Docker and why Docker alone is not enough if you want to do microservices. And then we will probably not talk about various kinds of orchestration frameworks. If anyone is really interested, maybe we can talk about that afterwards. But then this is the next session where we will talk more about Kubernetes, and we'll see how far we'll go. So I'm going to start off here with a little disclaimer. And I will be talking about a lot of different technologies during this presentation, and unfortunately we won't have time to cover everything in detail, and there is a lot of things that you can look into here. But this is actually not an introductory talk. Like there will probably be some things here that you might not have heard about, but just ask if you have any questions and we can maybe talk a little bit deeper about something. But the main purpose of the presentation is to present the road that we took of migrating from a monolith to a microservice, and get an overview of what you need to think about when you're doing microservices in production. Okay, so Parkster, this is where I work, and we are a mobile parking solution company. So as an end user, you will probably use our app that looks something like this. And you can use this app to start your parking or extend your parking and stop your parking and so on. But this is just like one side of what we're doing. There are other sides as well, like front desk integration. And if you're like a parking zone owner, you have some backend interface to look at statistics and configure things and so on. So actually, if you just you look at this for like 30 seconds, then you think like, oh, how hard can this be? Like everything else, it's so everything is easy. This just takes a week, something to create, but it's actually a lot more complex when you dig into this domain. It's a pretty interesting domain as well. So why is Parkster using microservices? Well, first of all, let's look at what a microservice actually is. So I don't remember where I stole this quote from, but I think it's pretty good. So here it says that microservices is an approach to application development in which a large application is built as a suite of modular services. Each module supports a specific business goal and uses a simple, well-defined interface to communicate with other modules. I think this is a pretty good definition, if you will, of microservices. And microservices, at least from the developer point of view, probably came about because of the frustrations that people were having with a monolithic system. Like monolithic systems are hard to change, and they're hard to evolve and so on. And since they're hard to change and they're then it becomes hard to redeploy. It may take a long time. You do a little fix, but that fix may affect other stuff in this big piece of software. So with microservices, you want to decompose your big system into smaller parts. So that's the idea of a microservice. And I think that this is actually really important. I mean, when microservices became like this hip thing a couple of years ago, people were talking about, oh, a microservice should only be like 200 lines of code, otherwise it's not a microservice. And I've always been skeptical to that, because I think that, or at least in my view, I think that a good microservice should be exactly as large as it needs to be. It shouldn't be larger than that, and it shouldn't be smaller. So I mean, it has nothing to do with the number of lines of code, in my opinion. It should, solve one specific problem and do that well. That's, in my opinion, a good microservice. So, why would you like to do this? Well, one of the reasons is, it should follow this single responsibility principle, and that is good for many reasons. I mean, it's easier for you and simpler if you have like a smaller problem to put in your head. You can only fit so many things in your head. It's harder when you have this like very big system. And another idea with the microservices is that it should be more resilient to failure. So if one part of your system, one part of your big system shouldn't cause everything to crash. I mean, if something crashes, only that particular piece of the software should crash, and the rest of the system should continue working. And microservices should also be easier to enhance, and that kind of follows from the same principle, from the single responsibility principle. I mean, they're easier to enhance because there's not so much code. They're easier to understand, and it's also since they're easier to understand and they have their own life cycle, I mean, you can deploy them at their own pace. And this is kind of related to the resilient part. I mean, it should have low impact on other services. So a service should really be self-contained and easy to understand. Ease of deployment, we'll talk about that. And one of the nice things with microservices that you want to have is the freedom for the developers to choose technology. I mean, you probably shouldn't let this loose, and like if you're in a large organization, you probably want to have some architectural baseline or something. But in essence, you should be able to pick any technology that is suitable for the problem domain that you're working with, ideally. But there are, of course, also many reasons of why you should not use microservices. So one of the problems is that if you're doing microservices, all of a sudden you have a distributed system, and distributed systems are hard. And all of a sudden you will end up with like remote calls instead of having calls that just is in memory, and that's it's tricky. And also your system will most likely become eventually consistent. And it's really hard to have like a distributed system, and I would almost say impossible to have a fully strong, consistent distributed system. I mean, that's something everybody wants to have that, but it's really hard. So what this means, but you would like to have this eventual consistency as strong as possible. So you would like to have some sort of strong eventual consistency. But what you have to you have to take into account that messages can arrive more than once. So your systems will probably need to be idempotent. And your messages will arrive out of order as well, and you should be able to handle that. And this is tricky. And then of course you will have more operational complexity. I mean, before you had your monolith and you deployed this. I mean, that was that was pretty nice. But now you have a lot of smaller parts that make up your system. So you need a better you really need to automate things. If you haven't done that already, you need some sort of automation. You need this DevOps and continuous delivery and stuff like that. And it's also really hard, to find what we talked about. What is a microservice? How do you construct one? How do you what is the right boundary for a microservice? And that can be really tricky. And getting that wrong will, end up with, you will have some shoddy communication, and your system will be really slow if you get this wrong. And this is really a hard problem. And then, of course, you have to deal with partial failures in your system. Because if you have systems like communicating with each other, like if system A talks to system B and system B is slow or down, you have to be resilient to that. So system A don't queues build up and stuff like that. So system A will also crash just because system B is slow. So you have to protect yourself against all kinds of failures. Okay, so before we move on, I just want to make some definitions. Yes, does everyone know who this guy is? Yeah, at least. Yeah, that's Rishiki, the closure guy. And have you seen his presentations? Good. And for those of you who haven't seen, all of his presentations, you should go home after these 2 talks and watch all of them twice, at least, maybe 3 times. They're all very good. Yeah, I think this one is, or not, yeah, simple made easy. I think for me that's my favorite, and value of values. Those are really good presentations. But I will at least try to use these definitions of simple and easy that Rich Hickey is talking about during this presentation. So when I say simple, what I mean is that there is no interleaving of different things. I mean it should address one concept, and it shouldn't be complected with other concepts. So this is what Rich Hickey means by simple. And easy, on the other hand, is something that is close at hand, something that we know. Maybe I don't know, maybe you're a Ruby developer and you pick Ruby on Rails. So maybe you pick that because it's easy, you're familiar with that. But Ruby on Rails might not be the simplest solution. And this is important because developers has a tendency to pick something that is easy, something that we know. And so this is like a graph I stole from his presentation, but I think that this is true. So probably if you pick something easy, you will get going really fast, but then after a while it will flatten out. And if you have a larger system and a complex system, you will actually be better off if you have chosen something simpler in the long run. So let's look a little bit about Parkster microservices again. So now I have a little animation, so you will guess why we are moving away from a monolith. And now this is the monolith, and can you see that it grows and grows and grows? So it's kind of big now. So yeah, I don't know. This is the reason. Okay. So yeah, we started out as a monolith, and this allowed us to move very fast in the beginning. I mean, we were using something called Spring Roo in Java when we started out, and this is something similar to Rails, where you do scaffolding and generate a lot of stuff. And this is it's not supported anymore, so I think it's a dead project. But it had it was easy. We knew Java, and this was we got things up and running fast. Yeah, easy. And it also, it allowed for experimentation. We didn't know this domain very well. We had to be able to experiment. And I think that this might actually be a good thing. Like if you're getting, you're a startup, and you want to, you need to learn your domain. You need to learn what is it that you actually want to do. I mean, if we start off by, doing too much of technical things like operations and spending all days with Jenkins or other stuff, we won't get any work done. The most important thing, when you're a startup, you need to get things out fast that works. You need to try out ideas and be able to refactor fast. But we definitely have run into problems with this approach. So we had this, this is a classic example. The boundaries in the monolith are really blurred. We didn't know the the subdomains that we had in this context. So there's like this typical, like you have a person, and this person is like used in many different contexts. So I don't know, it may be used in payment and order and invoice, and our core domain. It's shared between all these different contexts. So it becomes really huge and hard to reason about. And that it makes the system complex. It's not a simple system. And I mean, this works when the system is like, when it's small it works, but when it grows it becomes really complex. So it takes longer to add new functionality. So this was one of the things that we were suffering from. But another thing that it was difficult to keep up with new libraries. Since we were using like Spring Roo, it had some dependency on AspectJ, which had some dependency on the Java version. So we couldn't use some libraries that depended on other versions of AspectJ, and it became really hard to upgrade our core frameworks like Spring. It took a very long time, and it was really painful to do that. But if we want to like have some retrospect about this monolithic thing, sure. I mean, you can always do things better when you look at it. That's always the case. But I mean, I still think that Spark started off with a one-man show. So I mean, to go too much, focusing too much on splitting the domain and blah 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 blah. I mean, that would have taken too much time to get up to speed. So I still think that, I mean, this was probably a good idea when you look back at it. And it's also, I think it's easier to do this decomposition correctly of your big system if you have an idea of if you understand your problem better. Okay, so let's look a little bit into the organizational aspects of doing microservices. And this is our new office in Lund that we're really proud of. It's actually it's a great place, and but you may see that it's not like we're not a big company. We are 7 people working with this project. So I mean, we haven't run into all of these organizational or team issues that you may run into if you're working at a larger organization. That will be completely different. I mean, we are sitting very close to each other. We can talk to each other. We can have direct communication, and that is much easier when you're implementing something like this. So it will be much harder if you're working in a building like this, like in a bank or something similar that has something fancy like this. So what you typically do, or what you typically should do, is to organize your teams as independently as possible. So quite possibly you will have one team that is developing one microservice. And not only developing, because the team should be fully responsible for this service. And that means that you need to deploy it. You need to make sure that it's up and running. You should be the one that wakes up in the middle of the night if this service goes down. You shouldn't just develop it and hack it and then throw it over the wall to some DevOps team, because you should be responsible for this yourself. And this may seem scary, but it also gives you a lot of freedom, because you also need a lot of freedom in order to do something like this. Your team should be it should be possible for you to choose whatever language you want to have, if you can argue for it at least. So this guy is Ben Christensen down there, and he's worked at Netflix. I think he's moved to Facebook now, but I think he has some good litmus tests about organizations and microservices, and he has a good talk called "Don't Build a Distributed Monolith" that I can really encourage you to check out as well. And he has some questions that is you are required to answer yes to these questions if you are doing microservices correctly at your company. And the first one is that, yeah, you should be able to, as a team, choose, you know, the language that you feel is adequate for this particular problem, without convincing a central authority. So this is one thing that you need to do. And you should also be able to choose the concurrency model that you want to use in this microservice. So this might be, maybe it's good enough to have some thread-based model, or maybe you want to use actors or RX or fibers or something. You should be able to do that. And the protocol that you choose inside of your microservice, should be different to the one that you present to the outside. It's important not to have like these highly coupled binary protocols for integration, because that will not be a good choice, like Java RMI or something like that, where you're really coupled to the language inside of the microservice. So that is something that you want to avoid. And another thing that you should be able to answer yes for is temporal decoupling. And we all know that even if we write the perfect software, after a year or a month, our world moves so fast. After a while, this won't be the perfect code anymore, because things around us change, the world change around us. We get new libraries, or new frameworks, and new maybe, I don't know, Tomcat was the hip thing, and now it's Yeti or Undertow or something. You should be able to adapt, and you should be able to upgrade libraries without be afraid that you will affect like your core system or other services in your big system. And you should also embrace like this DevOps culture. This is really important. I've said that before, but you need to be able to deploy frequently. And yeah, it's like you cannot really talk about organizations without mentioning this guy, Conway. And he has this famous quote that says that any organization that designs a system will inevitably produce a design whose structure is a copy of the organization's communication structure. And what this means is that your organizational or team structure will very likely affect the software that you're building. So for example, if you're like developing a compiler and you have 4 different teams, you will most likely end up with a 4-pass compiler. You can Google for this and you will find a lot of different articles online. So this is exactly what famous microservices companies like Netflix, they know this, and they adhere to these principles, and they try to structure their teams around the services that they have. So that is also really important. So I stole this picture from Martin Fowler's website, and I think this is can summarize it pretty well. You should have some level of maturity in your team in order to do microservices. Otherwise, you will probably have a good chance of failing. Okay, so let's go back to monolith to microservices. How do we actually how do we get from a monolith to a microservice? So one way is of course to let's just throw this thing that we have, let's throw it away and we rewrite everything. That's great. We've all wanted to do that, I suppose, many times. The old code just sucks. Let's rewrite it in something new and better. But I think that if you do this, it's quite likely that you will, you will encounter the same problems that you had before, and you might not tackle them, so much better in this new shiny version that you have. You will have a lot of trouble. But even worse, it's quite likely that, the old system must still be able to, function while you're rewriting this, new shiny thing. And now maybe you have 2 different systems that you need to, manage. And that can, be really time-consuming and hard. And the old system may be, still evolving, and you need to do bug fixes and so on. So what I would do is to try to find these boundaries, these subsystems of your domain. Try to find them and try to find your core domain. Try to find what is it that really what is it that you're doing? What is it that really makes your company excel compared to other companies? And maybe so one way is to start with this piece of technology. But another way, and this is, I believe, is really a good way of doing things. Like if you get a new like the business comes and say that we should implement this new thing, and you think like, okay, well, this new thing, I mean, this it makes a pretty good this new service will make a pretty good microservice. So I mean, this is also a way to start. So like if you get this new requirement, I mean, you can maybe start with this, and maybe it's not like if something goes wrong, maybe it's not the end of the world. I mean, you can try this out and experiment and see if this is something that will benefit you. And I also think that one way, if you know that you want to move in this direction or maybe rewrite something, one way is also to really look at your maybe core domain and try to find what are the events, what are the things that are important to this domain that I want to share with the outside world. And maybe you just start sharing these events. Like for example, in our case, that might be parking started or parking ended or parking extended and something like that. And really, this is also a really good way to really understand your domain, because even if you have been working with a project for a long time, you may not actually have a clear definition of what the vocabulary that you're using. I mean, what does it actually mean? So this is a really good way of both spreading your distributing these kinds of messages to other systems to consume, and also to get to know your domain better. And and there are several Okay, sorry about that. It was not my fault, I hope. Okay. Well, one way of pretty fast getting to know your different events that you may have in your system is to use something called event storming, and so I can encourage you to look into that. And another good approach that can help us is domain-driven design and the strategic design patterns from domain-driven design. And one tool that we can use from domain-driven design is called context mapping. And context mapping is essentially, a way to visualize our current system. And here we will, you will see. I mean, here is an example of some bank application, I suppose. And they have like this trading system and some online banking services and expense tracking. And there may be different teams working on these services. So in the context map, you can easily see that the relationships between the different services and how they relate to each other. So for example, here we have a conformist relationship. So that probably means that in this banking domain, the web user profiling service here or team, they have to conform with whatever the banking team is doing here. I mean, they have nothing to say. They just, if they make any changes, okay, we have to conform to their changes. So, so this is a good way if you're in a larger organization to really, get a feel of what is it that we're actually doing, what is the relationship of all of our services and teams. And there are a couple of good books about this that you can read if you like. Okay, but let's look at a little more concrete example. So in this example, this is like our monolith, and we have our phone here that makes a request. Maybe he wants to park in at this parking zone. So what happens, and yeah, here we have another, like this is a microservice that is running standalone with its own database and its own data. Yeah, so what you could start off doing is, send, when he is parked in this system here, publish this business event. Parking started, for example. And typically you would publish this to some form of queue, and then this other system will, integrate and, builds up its local state or projection from these events that you're publishing. And yeah, and there's actually a lot of different issues, technical issues that can happen here. I mean, this is like the integration part of microservices from a technical perspective is actually what's, this is where the hard problems are, from a technical perspective at least. So I mean, you have like if you're migrating, you want to have consistency between your queue and maybe you have a local database here. And how do you do that? Do you use some kind of two-phase commit or some distributed transactions, for example? Or how can you guarantee that, if something bad happens to this queue, that we will still be able to deliver the messages later and we don't end up with an inconsistent state? And this can be, really hard. Yeah, okay, so in this example, this traffic warden microservice builds up its projection, and then the traffic wardens that check if you're actually do you have a valid ticket for this parking zone? They will query this system. But yeah, here we'll see another example. This is our what's it called? Interactive voice response system. So you can phone it. If you don't want to use our app, you can phone this service and hear a nice well. I shouldn't say nice, at least a voice. So you can use that to park in as well. And that communicates with this core monolith and also sends events. But things can go horribly wrong if you have this kind of setup. So for example, this is not a good thing, right? I mean, something burning is almost never a good thing. So, and if we're not careful here, like I said before, we have to be careful with these partial failures of the system, because otherwise we might have maybe we have some queues here, and we have a lot of concurrent users, and we fill up these queues, and that may lead to out of memory errors or buffers filling up or other things happening. So if we're not careful, this can actually happen, and this is not good. And this is it's a nice app, and this is some form of device, and yeah, they're nice to look at, but without the server, I mean, they're not very useful. You might argue, at least not from our perspective as backend developers. So you should protect yourself, and what this thing here should symbolize is a circuit breaker, and this is a very popular pattern that you use if you're if you're communicating across a network or something like that. So this gives, and this is Hystrix. We're a Java shop, so we're using Hystrix from Netflix for doing this. So this gives you like a first class concept to reason about failure modes when you make these kinds of remote connections to somewhere. So for example, here we do a query to get give me all your currently parked in cars at this parking zone. So if our core server is down, which is bad, then we should at least return something. We should return maybe an empty list or something like that. So that at least this interactive voice response system can kind of work and not just fail. So that's something that is really important to think about, because failures, at least if you run this on scale, I mean, failures will happen. That's just a mathematical proof was likelihood mathematically. It's very likely that you will run into these issues. But there are other things as well that you must consider. For example, now if we have decomposed our system and we have like our service. So how do we actually deploy it? I mean, if you can see this gray box here, this should represent a node. But I mean, what should we install on this node? I mean, maybe we're using Java, so should we? And of course now we have many nodes. So should we install Java on all of these nodes, so we can deploy traffic warden to whatever node we have in our cluster? But what if we have some other service that requires a different version of Java? And I mean, which version should we install? And maybe we have some other runtime. Maybe we have Closure or something. And I mean, should we, or some other runtime that we need to install? Should we install this, on all nodes in our system? So this is where Docker comes quite handy, actually. And how many of you know about Docker already? Okay, so that's like everyone. So yeah, it's essentially like this, like a container, virtual machine that you can use to package all of your code and your library and all of your dependencies and your runtime environment. So Java, for example, and you can like ship this container to a server, and it will behave, at least in theory, exactly the same way on your production server as in your test environment and in your local machine. And what's good with Docker is that it's more lightweight compared to other virtualization techniques, and it's immutable. And this is really good, because if you start a container and you write something to the disk of this container, it will be lost. Not necessarily, but at least by default it will be lost. And it builds on open standards, and it's it's secure in the sense that if you are in this container, you shouldn't be able to get out of this container and like mess up the host environment and something like that. That should not be possible. So a difference between Docker and a virtual machine, you probably know this already, but it's more lightweight, so we don't need an entire guest operating system in Docker that we need in these traditional virtual machines, and we don't need a hypervisor. And the hypervisor, is this program that allows the multiple operating system to share this one host. But we don't need that if we're using Docker, and that is a good thing. But in Docker, you still need an operating system, but typically the OS is very small. So in our case, we're running like a really small Linux distribution called Alpine Linux, I think, that is only 5 megabytes. And that is pretty cool. So with Docker, what it allows us to do is to encapsulate the runtime and all the dependencies and everything into this container. And you can actually incorporate state as well, if you like, and that makes sense for certain kinds of services, but for most services you should keep state out of Docker if possible, I think.
Do you actually deploy Haskell?
No, it was just cool to have it on a slide. So what Docker gives us is these reproducible builds, and it's very it's quite cool, because you can test things out locally, and then you should be certain that it works in production as well. And you can actually debug at least some production problems. You can debug that locally, so that is pretty cool. And you got no problem with the configuration drift. You know that the VM that you run in your Docker container will be the same VM that you run in your production server, and so on. But yeah, we talked a little bit about that before as well. And what you want to have is some form of continuous delivery. So this is just a view of our continuous delivery platform. That for each commit that we make to our Git repository, we build this Docker image, and push this up to our private Docker registry, and then it gets deployed to our test environment. So the test environment is always up to date with the latest commit things. And then we just we click this we click this button here and we just deploy it to production. And that works pretty well. And what's pretty cool is that our Jenkins server actually runs in Docker as well. So it's like a Docker in Docker. And this is pretty cool because you can make if you want to make like big changes to Jenkins, you can just grab the whole image and pull it down to your own machine, and then you make these like hard changes and you fail and you start over. And then where you're like happy with your changes, you push it back to your server, and everyone is happy in theory. But this is really difficult, and I would definitely look into some services instead, like Travis or something, instead of trying to do this yourself. Or read this blog that I created. That will really help you, I think, if you want to go down this route. But one really cool thing with Docker is actually integration testing, and this is actually great in Docker. I'm sure that you've all been like, if you've been in a large monolithic system or worked with a large monolithic system, you may know that the tests they take forever. They can take like 20 minutes, 30 minutes to run all of your integration tests. And I've seen many times people to make a change, and then you don't want to ruin it for all your colleagues, so you run all of these tests locally before you push something to Jenkins, and you just sit there, okay, blah 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 blah. You wait for like 20 minutes. Then it failed, and you have to start over. But one thing that is really simple to do with Docker is that now you have just these immutable containers. So you can easily just create a container and copy all of your source into this container, compile it, and then you run your tests. And now your source is now immutable, so you can continue hacking with your local code while the tests are running in background. And that's a good thing. And we have this script that we have for all of our services, and this is the very same script that is executed by Jenkins. So if it works locally, it will work on Jenkins, unless you have the flaky tests and stuff like that. And this is also really cool because it's no hassle setting up a new environment. Everything is just Docker. You don't have to download 10 different databases and cripple your Mac or something like that. It's with Docker you can just like get started very quickly. But typically you want to run multiple containers with Docker. So in this example we have our web app, but it needs a Redis database as well, for example when running the tests. So what we used to do was, and we're still using this for our tests, we're using Docker Compose, which is this declarative YAML format for essentially an easy way to get several Docker containers up and running at the same time, and it can figure out the dependencies between your containers. So here it understands that Redis must be started before the web app is actually started. So this is we're using this for integration tests, and we used to use this in production as well, actually. But let's talk a little bit about why Docker alone is not enough. So, we had a pretty, before moving, as you all know, to Kubernetes, we had a pretty decent setup. We were running in the cloud, and we had like this one script that could start up a new cloud server and provision it with all the stuff that we wanted. So, for example, installing the right version of Docker daemon and Docker Compose, and setting up and installing firewalls and unattended upgrades, and new relic agents and so on. So that it was really easy, to start up a new server, and also provision the servers. So if you wanted to, upgrade the Docker daemon or something, that was also Ansible was used to provision the servers. So that it worked pretty well. But the problem here was that in our Jenkins build pipeline, we told Jenkins to deploy traffic warden to server X, server U1, like a named server, and we told it to deploy our other services somewhere else. And so that was really one of the problems. So when we actually deployed a new version, we executed a little script on the server that's restarted and downloaded the latest or the Docker image that you specified in Jenkins, and then we also deployed like a zip file with scripts, and so that we knew which firewall ports should we open up to the outside world and so on. And it worked pretty well, but then something like this can happen. The fire comes back, and now this guy over there, he's I mean, he may look happy now, but he's not so happy when Pingdom wakes him up in the middle of the night. So and this happens. Server dies, and what we want is to be able to have our cluster to somehow deal with these kinds of failures automatically. And of course there are other things as well. One time our cloud provider was DDoSed. That's not good. And there are other things like how many containers can you actually run on a server? Can you run 2 or 3, or how many? I don't know. No idea. We have to do like something in order to notice. So we wanted something that could help us out, and also help us out with scaling. What if we wanted to run like several instances of our containers? Now we had to do these things manually. So what we want is something like this, something that sits in the middle of our servers and our Jenkins server. So instead of configuring Jenkins to push this container into a named node, we just want to tell some magic framework that please just I want to deploy, send it a description like a YAML file, and just like deploy this service somewhere in the cluster that you find fit. So where that there are enough resources available that you can deploy this service. And if a server dies, make sure to reschedule this container somewhere else in the cluster. If a container dies on the server, make sure to restart it and so on. And we also wanted to allow scaling and stuff like that. So we started to look around for different options, and we investigated these 5 different frameworks or services. And this is what I what's it called, struck from the presentation, because I don't have time to go into all of these. But if anyone is interested to know more about any of these, we can maybe talk about it in the break. And Tutum, I think it's called drcloud now. They were bought by Docker. But all of these are, they were good, but we came to the conclusion to use Kubernetes on Google Container Engine. And the reason, if you want to cut a long story short, was that it felt that this was the most mature solution that we could find at the time, and it worked for all of the things that we tested. So and it's also if you're running Kubernetes on Google Container Engine, Google will also make sure that the master node. We'll talk more about this in the next presentation. But Google will make sure that the master node is up and running and always updated, and it will make sure that all your minions, as they're called, all the nodes that you're running in your cluster, that they are like have something that's compatible with Kubernetes, and they you will get monitoring and aggregated logging and all of these kinds of things. But we'll look into that in the next session if you're still interested. Kubernetes is a way to manage a cluster of Linux nodes, and you can regard it as being a single server. That's the goal of Kubernetes. And okay. So this is I haven't prepared this part of the talk as much as the last one, so we'll see how it goes. But okay, so what's cool with Kubernetes is that you get a decade of Google experience of building these kinds of systems and clusters essentially for free, because Kubernetes is open source and it's on GitHub. And I mean, you can, and I've done that as well. I mean, you can file issues if there is something wrong, and you can like follow everything on GitHub. So that is pretty cool. And Kubernetes is also it supports multi-cloud, both in the sense that this is not like coupled to Google. There are several companies that are working with Kubernetes on GitHub, so you can run Kubernetes, you know, on your own in your own data center or on your laptop if you like.
That will be the third time.
Thank you, Mikkel. Okay, but you can also run this on Google Google Container Engine. So they have this like as a service, which is kind of nice. And yeah, it's also at least if you're running outside of Google Container Engine, it should be possible to run this on multiple cloud providers, for example, simultaneously, or in your own data center and in a cloud provider. So that should be possible, and it should be better as well in the future. They're working with something called Kubernetes that will support, you know, more what do you call it? You know, if you have two data centers that are far away from each other, that is, you know, a whole different set of problems, you know, with latency and stuff, than if you have data centers that are, you know, close by or just different availability zones. But Kubernetes supports rolling updates, both of, you know, applications and services that you run on Kubernetes, but also if you're using Google Container Engine, they also have rolling upgrades of the entire cluster. So, and that is a really nice feature to have. So at least if you have multiple instances of your containers running in the cluster, it will not, you know, affect the system, hopefully. And yeah, they have built-in service discovery, and that works really well. And they have support for auto-scaling, and this is, I think it's, they just released a new version 1.2. It was released last Thursday. So I think this was in beta before 1.2, but I think that now it should be production ready. Yeah, production ready. So Kubernetes should have been production ready since you know, the summer, since last summer when they released 1.0. The current version is 1.2, but I suppose that most are still using 1.1 since 1.2 is so new. And yeah, it has a lot of features, and more features are coming to Kubernetes. And yeah, as I said, it's open source, and yeah, besides Google, I mean, we have other companies like Red Hat, Microsoft, CoreOS, and Docker, and Mesosphere, and, you know, I think, yeah, I don't know, yeah, no, let's skip that. And this is actually quite nice with Kubernetes, because, as I said before, we were investigating some different alternatives to Kubernetes as well. But one cool thing with Kubernetes was that they're completely open with their, you know, future plans and their roadmap. You know, they publish their roadmap on GitHub, and, you know, everything is on GitHub, and this is, you know, this is really nice, I think. And I mean, it's also built to be extensible. So if there's some part of Kubernetes that doesn't fit your, you know, your company for some reason, like if you want a different scheduler or something, you should be able to replace this scheduler with something else. And that is, even if you don't use this, I think it's, you know, good to have that they have this, that they've thought about these things. And it also supports, besides Docker, it also supports Rocket. I've not used Rocket myself, and I doubt that the Rocket support is, you know, on par with Docker, but they have some sort of support for Docker at least. And I think Google is also sponsoring Rocket, so I think that the support for Rocket will increase in the future. And this is just what I think is pretty cool. I don't know if anyone else thinks that this is cool. This is this guy is working on Kubernetes. Eric Brewer. He was like the founder of the CAP theorem. I mean, he's like this hero, you know. Okay, maybe that's just me. Okay, so let's talk a bit about the concepts in Kubernetes. So if you know from the previous talk, we had this Docker Compose, where you specify that you want to run multiple containers kind of together, and this is kind of exactly what a pod is. So a pod is a way to specify multiple containers and have them deployed as a single unit. So this unit, I mean, if you scale this unit, you will scale all of the containers inside this pod container. And this is a very nice thing. So previously Google had something called Borg. So they have taken a lot of experiences from Borg, and I think they're still using Borg, or they are using Borg internally as well. But they've taken lessons from working with Borg for 10 years, and they're trying to apply what they've learned to Kubernetes. And I think pods was one of the things that they want to improve upon, and they have done so by making pods a first-class concept in Kubernetes. And then we have a thing called a replication controller, and this is what controls the replication factor for pods. So for example, if you want to have this pod group instance running on multiple instances, you use a replication controller to say that, okay, I want to run this in have 3 instances of this pod running somewhere in the cluster. And then they make heavy use of something called labels, and this is how many things work in Kubernetes under the covers. So for each pod you can specify labels, and these labels you can use, for example, to determine how load balancing will work, for example. And I will show you examples of this. And they also have a good networking model. I know that some other services similar to this, it can be tricky. Like if you have some containers that expose port 80, and you have one container that exposes port 80, and you have another container that also exposes port 80. You cannot run them on the same node. Some services won't allow you to do that. So Kubernetes does a lot of networking magic to get these things just working. You don't have to think about these kinds of things with Kubernetes, and that is really nice, I think. Then they have a concept, something called a service, and this is essentially like you can regard this as a kind of a DNS. So if you have pods that want to talk to each other, you can expose a service, because you typically don't want to talk to between pods directly, because the instances can go up and down. You want to talk to a cluster of pods, so you deploy these cluster of pods behind a service, so the service knows how to route to the different pods. And a service can also be used to expose your pods to the outside world. So there are different types of services. Some services that are just like internal, if you just want to have internal communication or something, and other services can expose things to the outside world. And then we have ingress resources that they're still in beta, but you can do like more advanced load balancing. For example, using if you want to route like by the host header, you may have the same URI to a service, but different host header in your HTTP request. You can actually route from the host header, or you can route, like if you have this Nginx configuration where you're like, this path should go to this service, this other path should route to another service. I mean, you can do these kind of things with an ingress resource. And so the architecture of Kubernetes looks something like this. So you have a master node, and this is, I say, a master node here, but you should of course have multiple instances of this. I think there's only one master at a time, but you should have failover if the master goes down. So if you run in Google Container Engine, they will, make sure that this master node is always up and running, and that's a nice thing. But if you decide to run Kubernetes, on your own data server, you need to, manage this yourself. But then you have your nodes that you have in your cluster, and they're called minions. And each node has a Docker daemon running. And here you can see that, there are some pods on each node that has been scheduled to the nodes. And each pod contains one or more container. So this is essentially the architecture. So what Google Container Engine will give you is this sort of like managed hosted Kubernetes. So you get this, the master node. Google will take care of the master node. You will also get, a problem that you have to deal with when using microservices is that, all your services, they produce, logs. You don't want to, use SSH into every container to, see the logs. You want all the logs to be aggregated, and Google will handle that for you. So you just log to the console, and Google have some fluentd daemon running that will, push everything to their servers, so you can view them from the UI. And they also provide monitoring, so you can monitor your cluster, and you can monitor individual containers. We'll see if it works. It's still in beta. And it also, when you run it in the Google Cloud, you get access to all Google's services like Cloud SQL and data flow and all kinds of BigQuery and stuff like that. And so you can integrate with all of these services. So that's that's nice. The pricing is also, if you're running a small cluster, like I think it's up to 5 nodes, then Kubernetes itself doesn't cost any extra. You only pay for the nodes that you have. But if you run larger cluster than 6 machines, then you pay some amount of money. And Google also offers support if you pay for the support. Otherwise, you have to ask questions on Stack Overflow and Slack. But if you want rapid response, you should probably pay. So now my intention is to run some sort of a demo, and this demo I've stolen it from a really great guy. He's what's he called? Kelsley Hightower at Google, and this is essentially his demo, more or less. And what I will show you, I've built Hello World app that we will deploy to Kubernetes running on Google Container Engine, and we will use some of the command line tools to do that, and we will we will see how we can scale it up and down and so on. Yes, and Google also provides a private registry for Docker images. So you push, when you've created your Docker image, you can push it to Google Container Registry. So that is quite nice as well. So the binaries are stored on Google Cloud Storage. So that's pretty good. And now I probably should have prepared, because I need internet, but I haven't prepared. So this will take a little while for me to get internet. Let's see. Oh, you can't see this. Blah, blah, blah. Waiting. Come on. Maybe we can use this one. Okay. Seems to work. Let's see if I can access some page. Hey. Okay, good. Okay, so let's see. So if we look at, oh, you can't see this. Oh. Okay. So if we go into the source code, I will just show you, I mean, the code very briefly. This is, I don't know if you can see this, but yeah, it's like a very simple, like a web resource that just returns hello world version 1 when you call it. So it's nothing fancy, and it logs something to the console. So this is the nice microservice that will be deployed. Perfect microservice, one business capability, right? Okay. So let's start off with looking into. Here we go. Oh, I had it open already. So this is, I don't know if you can see this. So this is the replication controller that I was talking about. And currently, I think this is not optimal, but you specify the replication controller and the pod in the same YAML file. As far as I know, there is no way to separate them unless you do something yourself. And it's a little bit confusing. But essentially, this is like the YAML file. So yeah, we say that it's the kind is replication controller. We give it some name. We call it demo 1.0.0. And here we define some labels that I was talking about as well. I will show you how it will look. So this is on, yeah, and then we have a specification for this replication controller. So we say that we want 2 replicas. We want 2 instances of this pod running in our cluster somewhere. And here we specify a selector, and we will come back to this selector, but this is really important. We specify the name demo and the version 1.0.0. And this is, we use this selector because we want our load balancer or our service to identify this particular pod. So this is why we specify the selector, but we'll see how that works. Yeah, and then essentially down here we have the actual pod. So here we say that the name of our container should be demo, and we should use this image, Kubernetes presentation 1.0. We specify a liveness probe, and this is for Kubernetes to know if this service is up and running. So here we say that we want Kubernetes to do a GET request to this path, and we want it to make this GET request on the external port. And okay, if we go to port, you can see that we're exposing port 3000 from this container, and we give it a name, external. So now we can refer to this port by the name. We don't have to, repeat 3000 on, all over the place. And this is really nice. So here we say that, yeah, you should run this like liveness probe on this port, and wait, before you do it the first time, wait 10 seconds, and then, have a timeout of 1 second. It must respond within 1 second, otherwise consider this pod to be non-alive, not working. Yeah. Okay, so that's the replication controller. And so if we try to, now I'm just copying here. But so what you typically do is that you have something called, I mean, in Clojure you have lining and a root or something, but you build your Docker image, using your build tool or some script or something. And yeah, that takes a little while. But once you have this, as you can see, now it's creating the jar file. And it should create, yeah, I don't know if you can see this, but down here it says that it has now created a Docker image with the code and all the dependencies and put that into a Docker image. So, well, that's pretty nice. So now we want to, we want to make sure that we can actually, does this thing work? So we can try this out locally. So, well, oh, this is, sorry, the resolution is a little bit small. Okay, so let's try to run this locally first and see if it works. And now it has started up. So let's try it out. It doesn't work, you bastard. Let's see if do something like this. Yeah, because I'm using a Mac and you have to use Docker machine if you're using a Mac. Yay! Can you see this? Really cool. Okay. So now we know that it works. Everything is fine. So now we want to deploy this image to Google, and we can do that by using this command. You issue. Yeah, can you see this? You run this command, but this takes a while, so I will not do that. I have prepared. Hopefully, I have prepared. Otherwise, it will be a short demo. So now we imagine that we have, we're pushing this to our private repository. Okay, and it will just, if you really want to see it, not hear me for 5 minutes, then you should raise your hand. Otherwise, we can continue. Okay, thank you. All right, so Kubernetes has the CLI interface. It's called kubectl. So kubectl, you use that for all commands that you want to run towards your Kubernetes cluster. So what we want to do now is to create our replication controller and our pod from this YAML specification and deploy that to Kubernetes. So let's try and see if this works. Yay, created. That's cool. So now let's go back here and maybe we can do kube. Can you use kubectl get pods. Yay. You should see here with the here we have 2 instances of our Hello World service running in Kubernetes. Okay, now they're running here and they seem to be working. I hope it says running. Okay. Oh no. So now but yeah, we cannot access these services now, externally. These are internal, pods running in our cluster. But we want to expose them to the outside world. So this is where services comes into the picture. So if we look at our service, whoa. So this is also a YAML specification. So this one is of kind service, and it also has some labels, so we can identify the service. And we declare the service to be of type load balancer. And this means that when we deploy this, or when we create the service on Google Container Engine, it understands what type load balancer means. And under the covers, it will create a load balancer for us somehow. And now comes the important part, because we want this load balancer to access the port, the external port that we defined here. External, and we give it, this could be any name, but this is just the name of the port that we provide to the outside world. We expose port 80, with the name external as well, but this could be another name. But I just put this name here to be the same as this one to confuse you. But okay, so we expose port 80, we call it external, and we route to the external port, which is defined here, which means 3000. And the selector, this is the important thing. We want the selector to be demo. So we want to route between all of our pods that has a label with name equal to demo. And we have that here. Here. In the selector in our application controller. We have defined demo and version 1.0, but we don't care about the version. And there's a reason for that. But we could specify more key value pairs here at the selector level if we want to make sure that we only route between 1.0.0 versions. But here we only route to the name demo. Okay, so let's create, let's create this service. And this takes a little while. Okay, now the service, now it has created a service, but it's asynchronous, so we have to wait for the service to come up. And we can do that by using kubectl get svc minus watch, I think. Yeah, because now now it will watch for changes to, this is a shortcut for listing the services. You don't have to write service, you can write svc. But now we wait, and we wait for the load balancer to start up and to assign an external IP. And that can take a little while, a minute or so. So maybe if you have any questions, now is a good time.
The load balance service, is that specific when you run on Google Cloud Engine, or can you run that locally as well? For example, if you deploy it to Amazon.
Yeah, so now the external IP. No, but the question was, is the load balancer type specific to Google Container Engine? And I think so, actually. I'm not sure. I'm not 100% sure, but I think so. But at the same time, I don't think that it has to be. I think that you can create some Amazon-specific hooks into this. So you create an Amazon load balancer, but I'm not sure if that's supported. But you can probably look it up somewhere. Okay, now we have our external IP. So let's see if this works. Can you see this? It's quite cool. So now we have our super scalable microservice up and running in the cloud. And if it dies, it will restart it. Okay. So then I want to show you how we actually can scale it. So I copy this command here. So if we decide that we have so much load on this popular service that we need 3 replicas, we simply scale it like this and say that we want 3 replicas. Okay, so let's do that. And it says that it's scaled. So that's a good thing. So let's see if it really is scaled. Yeah, it seems to be starting up at least. So let's see here if we do kubectl logs. Yeah, now it's up and running. This is the logs. Okay, so that was pretty cool. So now we can scale it up and down quite easily. Yeah, so let's look at this. So now I'm gonna start a little curl. So now you should be able to yeah, now this little curl script just yeah, it every half a second it makes a request to this service. And what I want to show now is that you can do this, like, yeah, now we want to build you know, our new cool version of this. You know, this is so hip, so let's continue with this like trend that we've started with this, you know, cool, you know, services that we have. So we want to yeah, maybe we want to change this to Hello World 2. Okay, so this is the next generation of our Hello World service. But we're not sure if this will be as popular as the old one. So, you know, we want to start off, you know, a little bit, you know, take it a little bit easy. So let's try if we just, and now, you know, you build this the same way and you deploy the Docker image and blah, blah, blah. But I've already done that, so we don't have to look into that again. So let's just start one instance. Let's see if it is one instance. Oh, no, it's 5. 1. So let's try to start one image or one instance of this number 2 service here. So let's see. Yeah, so it's up and running. Oh, can you see? Yeah, good. That's pretty cool, right? This is, you know, now we could, you know, try this. What is it? Every 4th request should go to version number 2 or something. And this works because, you know, we configure this service to have the selector for the name and not the version. So this is why it works. Because the version is different, but the name is the same, so the selector will find it. Okay.
I guess you can also target when you map the pointer, so you can target different portion of the version and provide all the APIs.
Yeah, yes. Yeah, so the question is, I mean, yeah, this is very flexible. I mean, you can use these labels, they're actually, I mean, they're very simple and you can do quite powerful things with them. So exactly, you can route, like, you know, if you have if you have different versions of your services and you're not backward compatible and blah, 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 you can have different services for those kind of things, for example. You can do a lot of things. But let's stop this thing. Yeah. Because now I will show you how we can do. Let's do a rolling upgrade, because that's pretty cool. So now we have decided that well, yeah, this new version. Okay, we're ready to, you know, deploy this to the masses. So what you can do, or this is actually what you used to do until last Thursday, because now they have a better way to do that. So I will actually show you some legacy stuff here, but it still works. And I will show you why it's, or yeah, I can explain why it's legacy. But okay, so here you issue a rolling update, and then you say that you want some update period of 5 seconds, and this means that we will have a, you know, delay between every update. We will have some sort of grace period. Wait 5 seconds. Usually this is a bit longer, but now we wait 5 seconds until we try to deploy the next version. And we want to upgrade from our replication controller demo 1.0.0 to this, you know, 2.0.0 here. So let's try this. Yeah, so now it says that it's scaling up from 0 to 3 and blah, blah, blah. It's at the same time scaling down 1.0.0. So now we should see more 2.0s here. And in the end, we will hopefully see that we will only have 2.0s and we will have no downtime. And we can actually view the logs. Because yeah, one pretty annoying thing is that you cannot, as far as I know, you can only get logs from a single pod from the command line. but you may want to get like logs from all of your pods, aggregate from the command line. I don't know any way to do that. So I've written my own script called kubetail. So you can download this from GitHub if you like. So you can do GitHub demo, or sorry, kubetail demo, and you will see all the logs aggregated. So that is pretty good. But now it seems like it's done. So yeah, now we only have 2.0 here. So that is pretty cool. But the problem with rolling update is that it's, and before I say that, it's pretty, I mean, if things fail here in the middle, you can, roll back and stuff like that. But the problem with rolling update is that it's client side. So, if something happens, my machine were to die in the middle of this, while we're executing this command, the rolling update will, stop. So in the new version, they have a concept of deployments. So it's like this YAML specification as well. So you specify how the rolling upgrade should behave, and then it's executed on the server instead. So it's actually much better. And I think there are more features than what you can do with rolling update as well. So I think that's a good improvement. Okay, so I think that was actually the demo. So I'm not sure if you're tired, or maybe because now the last part is about the demo hopefully looked pretty cool, and like let's just jump aboard and rewrite our monolith, which you shouldn't do. But everything is not perfect, so I mean I can go through this fast so you don't fall asleep. But yeah, it's there are some caveats with the Kubernetes, and so one thing is that how do we get these like so if we have configuration files, how do we get our configuration files into the container in Kubernetes? I mean, one way, because what you usually have is that you build one image and you reuse this image in your test environment and in your production environment, and if you have other environments as well. It's the same image, but you have a different set of configurations. And this was one thing that we had really trouble with, because there were not good support for passing in like environment variables from the outside into the specification. And so I wrote this like bash script, templating bash script to get this working. But it's a good thing is that they have actually solved this in Kubernetes 1.2. So there they have something called config maps, exactly. So this is, if you are using, you should, if you are thinking about using Kubernetes, you should probably wait a couple of days until they have, upgraded the Kubernetes version on Google Container Engine, so you can avoid some of these hacks. But this will be better in. I know that it's hard to wait. I know, but just. Yeah, it should be better in Kubernetes 1.2. You can, never mind. Another thing that we ran into, we're using this, they have a SQL database that you can use, it's called Cloud SQL. And they have, if you're using it from App Engine, they have really good support for, you don't want to expose this, server to, the entire world. You want, like in Amazon, to have like security groups and stuff. And they have similar things on the Google Cloud. But if you have this dynamic environment, you don't know the IP address of the actual nodes that you run in your Kubernetes cluster. So how do we lock this? How do we lock the Cloud SQL server to only be accessible from Kubernetes? And they had no really good support for this. So luckily there was one guy who had hacked something up. So you can some little container that pulled the IP address of the cluster and made some calls and upgraded the configuration of the Cloud SQL server. So that worked pretty well. But I think they have and I blogged about this as well. But they have something. I'm not sure. Yeah, they have something called nowadays called Cloud SQL proxy or something, and I think that's the recommended way that they recommend today if you want to do this. I'm not sure if this actually works on the old version of Cloud SQL. They're releasing, it's in beta, but they have a new version coming out pretty soon. I'm not sure if the proxy works on the old version. We're using the old version, so, and this works fairly well. This is not a problem with Kubernetes. This is a problem, at least with all of our Docker containers. I mean, you want to stop a Docker container, or I mean, yeah, if a Docker container stops gracefully. I mean, if you're running like Java, you can add this shutdown hook, so you can gracefully, stop the container. But our containers didn't stop gracefully; they were just, killed. This is, I don't think this is Kubernetes' fault. Either it's our fault or Docker's fault. I don't know. But what's good with Docker is that you can specify this lifecycle hook. So you can specify, and this is very cool. I mean, you can specify like a script that you want to execute before the pod is stopped, for example. So yeah, we created a little script that killed the Java process and waited for it to die. So we have that on each pod that is running Java. And as we were migrating, from our previous setup where we had these named nodes and stuff into Kubernetes. And there, for service discovery, we were using like DNS, global DNS names. That was our way of service discovery back then. So that meant that all of our health checks and stuff like that, all of our management resources were behind basic authentication. And liveness probes doesn't support basic authentication. So either we had to rewrite some parts of our services to work without basic authentication, or you can actually execute the liveness probe. You can execute your own command as well, which is kind of neat. So you can, you can fall back to using curl in the liveness check if you want. I think this is pretty good, actually, that you have this ability. But then it gets worse. Okay, so I actually showed you this. You can only log, as far as I know, from one pod. But you may want to log from multiple pods from the command line. And you can use this kubetail script that I created if you want to do that. And there are the links. And this is what we just showed in the demo. But I showed you this rolling upgrade or rolling update. But the problem is, I mean, in Google you have something similar to, in Amazon you have this EBS, Elastic Block Storage. And in Google you have something called Google Persistent Disk. But if you're using a Google Persistent Disk, you cannot do a rolling update. Actually, that's not what I wanted to talk about here, I think. No, the problem here was actually, I think that's the next slide. But okay, that's a problem. You cannot do rolling updates on those if you have a Google Persistent Disk. Another problem is that if you already have a replication controller up and running, then you should do a rolling upgrade, right? Like the one we saw in the demo. But the first time we deployed our service, we didn't do a rolling upgrade. We just created the pods and the replication controller, and that's a difference. So like in our Jenkins server, I mean, it's, the first time we deploy from a Jenkins server, it should create it. The second time, it should do rolling upgrade. So this is a little script that tries to find out if we already have this service running. If so, it does rolling upgrade. Otherwise, it just creates it. And this, I think, is also improved with the Kubernetes 1.2 with the deployment APIs. At least that's what I hope. Yeah, and this is what I was talking about. It's inconsistent. It doesn't work if we have these persistent disks. I don't think that this works in 1.2 either. I think it's coming in 1.3. Yeah, and also this is a little bit awkward. We saw that the scheduler, it schedules the pods onto different machines, hopefully. But if you only have two, if you run two instances, for example, they may actually end up on the same node. Oh, okay, that was not good. this you can see here. Here we have 2 instances of the pod running, but they're deployed to the same node. That kind of sucks, because you want some form of high availability. But I mean, I don't know. I mean, if you have free, I've never experienced this if you have free pods, but sometimes, you know, randomly it just picks the same node, and that's not what you want, because then you will have downtime if you do rolling updates. So no, I take that back. It's not. You may not actually have that problem, but it's still. I think that it could be improved. Oh yeah, this was the most crazy thing. Yeah, I don't know where to start. I mean, it's this has taken a lot of time because, yeah, you know, you want to use HTTPS and SSL, right, for your services that you expose, and in order to do that, you need to use an HTTP load balancer in Google Container Engine. You cannot use this. If you remember, we set the service, we set that to type load balancer. What happens is that it will create a network load balancer under the hood. And that is quite cool. That means that you know, you can use other protocols than just HTTP to talk to your Kubernetes cluster. So that is awesome. But they have another kind of load balancer as well called HTTP load balancer. And if you want Google to do your SSL termination, you need HTTP load balancer. I mean, you could you know, use Nginx and stuff like that as well. And we knew that, in order to create an HTTP load balancer, you need to use this ingress resource that I was talking a little bit about. But ingress resource is in beta, and it doesn't support SSL termination, or it didn't support SSL termination until last Thursday. So now SSL termination should actually work. I haven't tried it, but this was a disaster. We hope that they will like get this out, you know, soon. I talked actually to some Google engineers, and they said that yeah, we will, you know, this will be improved very soon. Okay, so let's try it. But we had to do so many manual things to get this working. Yeah, blah blah blah. Create firewall rules and blah 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 blah. But hopefully, yeah, this will be better in the new version. Because yeah, this is horrible. Yeah, and we run into, you know, some other problems as well, some various bugs, and yeah, some various you know, smaller issues. I mean, they're working constantly with their services and improving things, but many of like the monitoring API, it's still in beta. So yeah, I should actually show that, but now I didn't, so now I don't have to. So, but I mean, you can like have this, you know, nice monitoring things. But for this, I mean, I couldn't get it working for the demo. So I mean, it's I don't know why. It's still working in our production and test environment, but for the demo it didn't work. So I don't know. So it's still in beta. Yeah, but now if you run home today and deploy your production system in Kubernetes, one tip is to use something called resource requests and resource limits. This is actually really nice. I don't know if you can see this, but this is, you specify how much memory is required in the cluster and how much CPU is required on the cluster for this pod to even be deployed. I mean, don't deploy it to this node if we don't have this memory or CPU left on the node. That is really nice. And also, so that is lower limit, but you also have the upper limit. If this service consumes more than 128 megabytes of RAM and more than 50% of the CPU, you should kill this. Something is wrong with the service. You should kill it. Yes. Is it possible to use Kubernetes for storage?
No, for monitoring resource application.
Do you mean the monitoring API or the? Yeah. Okay, now I know what you mean. Yeah. Okay, I know. Not sure. I don't think so. But from the monitoring, you can set up alarms and stuff from the monitoring API, so you will get, you know, alerts when the disk is you know, running full and stuff like that. And they also, I mean, there are more. I mean, you can. What's pretty cool is you can have a, you know, like a cluster of persistent volumes, and then you can have what's it called? I think it's called the resource claims. I'm not or volume claims or something like that. So you can say that I need a volume. I need I need 50 gigabytes. Just give me a disk that has 50 gigabytes, and it will get this disk if it's available. So you can do a lot of these things. Yeah, and there I haven't shown this, but you can do. Yeah, maybe I'll show it later. But there is a command called kubectl describe. And this is a really good command because if your pods are not starting for some reason, you just do kubectl describe pod and the name of your pod. And you will get a lot of details on why it doesn't start, for example. So that's a good thing to remember. And yeah, this kubetail script is also quite nice. And yeah, the Slack channel. I mean, if you don't pay for support, Slack is your friend. And Stack Overflow, because they have, they pay people to answer questions on Stack Overflow, and I think Slack as well. The guys who are working with this are active on the Slack channel, and also on the GitHub page. And I say this as a compliment actually, but I don't know. I think there's like 15,000 issues that has been reported on Kubernetes on GitHub, and most of them have been resolved. And I mean, if I as a small person, I add an issue to Kubernetes, and they will be really friendly, and they reply to you, and really they take your issues seriously. I mean, I think that's really impressive with the amount of stuff that they're actually doing. So yeah, Stack Overflow as well. So yeah, we are happy with Kubernetes. I think that we made the right choice, even though there are some caveats, and I think that in my opinion 1.2 is the actual 1.0 version. This is what should have been 1.0. But I mean, we knew that we were going to have some do some workarounds with whatever framework and service provider that we chose. And the Kubernetes, we did quite an extensive research before we chose Kubernetes. And it even though there are we need to do some workarounds. I mean, we are able to do our workarounds. That was not the case with some of the other stuff some of the other frameworks that we tried. So that's workarounds. Yeah, and the future for Kubernetes, I think, yeah.
The other frameworks that you investigated, so with whom Kubernetes fight with?
Yeah. So the question was, what other frameworks do Kubernetes compete with? So I mean, there is I don't know. There's probably 50 different. There are so many of these kinds of things now. This is an explosion of different alternatives available. But we looked into Amazon Elastic Container Service and Tutum, that is now called drcloud, and Mesosphere DCOS. Really, that's a really cool, but we didn't think that it was mature. For example, you couldn't do rolling upgrades on the cluster, and I mean, then you have to. I mean, what do you do because in DCOS you run stateful things as well. That's one of the cool things with the DCOS is that you can install these databases and HDFS and all of these kind of stateful things into the DCOS cluster. Really cool. But if you cannot do rolling upgrades and they're releasing new versions frequently, I mean, how can we keep up if we use these stateful things? If we don't use the stateful things, then it's probably you just create a new load balancer and you switch between. Yeah, I mean, there are ways to do that, but in Kubernetes that was built in. What else did we try? No, we didn't try Fleet. What was the other one? Do you remember? I don't even remember. Yeah, but of the ones that we tried, this was the most mature. Because, for example, with the Docker or with Tutum, the issue that we found there was that it didn't reschedule containers. If the CPU went up to 100% on the node, and there were some containers running on this node, it didn't reschedule these containers to other nodes. That's why we didn't choose Totem. And maybe they've solved it. I mean, we did this investigation in November, and that's I don't know, it's forever in this world. So they might have fixed that. But that was actually the reason why we didn't choose Tutum. That have actually been an easier solution for us, because Tutum is we were using like Docker Compose, and they are using Docker. Yeah, I think now they are actually using Docker Compose, or at least the same YAML file format as Docker Compose used. So would have been much easier for us to just use Totem. But because of that, we didn't choose it. And the reason, because that has actually happened to us in production, that we had run into this like 100% CPU, and the server just died. So we wanted that to work, but unfortunately it didn't work. But I think, if you can read that, there's a lot of things that they want to do in the future for Kubernetes, and I think it's really looks really promising. For example, I really, this Kubernetes, as I mentioned before, so you can have multiple data centers. Oh, that I should definitely mention. This is a really a big drawback of Kubernetes in Google Container Engine. You can only run it in a single data center right now, and that's not good. If the Google data center dies, our cluster will die. But you can put 2 clusters behind the load balancer. You can do that today. But I actually talked to some Google engineers, and they told me that in 1.2 they should have like this mini version of Kubernetes that should at least work between multiple data centers. So if they bring that into Google Container Engine, and I hope so, that would be awesome. That's a great way forward. So Google Container Engine is nice. So I still think, it's still pretty bleeding edge, I would say, but it's getting there. And with Kubernetes 1.2, at least on paper, since I haven't looked into it, I think many of the issues that we had should be resolved. So that is cool. Okay, that was the end of the second presentation. I have a third presentation, but I suppose that you want to go home.